Welcome back. In this video, we're going to take the next step. Now that we have learned how to draw Lewis structures, and then now we know how to take the Lewis structure, count the domains, and assign an electron domain geometry, one of the big five. Now we're going to learn how to assign the molecular geometry that's part of the VSEPR theory. I call molecular geometries the subsets of the electron domain geometry. On the screen here, I've got tetrahedral, and I'm showing you the three subsets that you're going to have to be worried about for the tetrahedral electron domain geometry. And the reason I have this on the screen right now is because I want to explain to you how molecular geometry is different from electron domain. The thing that they have similar is that all of these subsets of tetrahedral do have four domains. So these are all four domain geometries, and they're all three-dimensional. But a molecular geometry, or just a shape, and sometimes the AP curriculum just calls it molecular shape. The molecular geometry is just the shape you get from the central atom and the terminal atoms, so just the shared pairs. If you look at trigonal pyramidal here, the one in the middle, it looks like there's only three domains. But since it's tetrahedral, there's actually four. And what's missing is a big fat lone pair on top. When we talk about shape or molecular geometry, we're trying to ignore the electron lone pairs. They do affect the geometry bond angles ever so slightly, but it's just really an artistic kind of a thing. What do you see here from the terminal atoms and the central? The lone pair is just a couple of electrons sitting up here, not really affecting the aesthetics of the molecule. I hope that makes sense. It's very weird to kind of explain it. We're going to go back to our modeling software so you can see what I'm talking about more clearly. Okay, we're back in our modeling software, and I have the first electron domain geometry. We called it linear, it has two domains. This is a very simple geometry because there's really no subset, no different name subset. If you have this electron domain geometry and both of your domains are shared, then the molecular geometry, let me click on that name, is also linear. Okay, and it's symmetrical. Now the only thing we can do to mess with this geometry is to take away one of our pairs and replace it with a lone pair. Notice what that changed. It didn't change anything. We still have linear, it's still two domains, and then the molecular geometry is still linear, because ignore this shape over here and just look from purple ball to white ball, it's still in a line from each other. Now this shape is no longer polar. Sorry, it's no longer nonpolar. This is now a polar shape, and you would find the polarity by using the delta En that we did recently. Okay, so for linear, the only subset is really also called linear. Let's take that away. Let's put a lone pair back, or a shared pair back, and then let's put another one. So let's go to our trigonal planar electron domain geometry. The trigonal planar has two subsets. If all three of the domains are shared, so we have terminal atoms, if all three of them are the same, we have a nonpolar molecule, very symmetric, and this subset of molecular geometry, as you can see from down here, is also called trigonal planar. Now, if we took one of those away and replaced it with a lone pair, we have another subset of trigonal planar electron domain, and we call this bent, as you can see here. Bent, or V-shaped as it's sometimes called. This is no longer symmetric because the top big fat lone pair is more repulsive than the other two shared pairs. We still have pretty much our 120. What we're going to see here is that between the big fat lone pair and the terminal atom is going to be a little greater than 120, maybe a 121, 120.5, up to 122, 123. And then between these two terminal atoms will be less than 120. They're going to be squeezed together ever so slightly. Very small angle changes. But this is the second subset of trigonal planar. We have two, trigonal planar and then bent. Now I realize that as I hear myself talk that I may be confusing you. So let's go back and let's do this again. I want to make sure you understand what I'm saying. This is trigonal planar electron domains. And I am now telling you that this electron domain geometry has two subsets. The first subset is also called trigonal planar because all the domains are shared. If I replace that with a lone pair, this is the second subset of trigonal planar electron domain, and it's called bent because molecular geometry is the shape only made by terminal atoms and the central, and you see a bent or a V shape here. I hope that clears that up. I realize how confusing that probably sounds. All right, let's go to our next shape, which is when we have four domains. We call that tetrahedral. The tetrahedral, as I showed you on the opening slide, has three subsets, the first of which is called tetrahedral because all four domains would be shared. Let's replace one of the domains with a lone pair domain. We still now have four domains, so it's still tetrahedral electron domain, but this subset is called trigonal pyramidal. And it's called trigonal because when you rotate the molecule to put the big fat lone pair behind the central atom, we have the shape of a triangle. So that's where the trigonal comes from. And because it's three-dimensional shape, it's not a flat triangle, it's actually a three-dimensional triangle, so it's a pyramid. So that's a trigonal pyramid. The bond angles here are no longer 109.5. They're going to be between the terminal atoms now. For example, this angle right here is going to be a little bit less than 109.5. So usually between 104 and 109, depending on what these terminal atoms actually are. The next subset of tetrahedral looks kind of familiar to you. Again, ignore the mouse ears up top. This looks just like the subset we saw with trigonal planar. This is also called bent or V-shaped. It is a different bent from the trigonal planar version because the bond angles are a little different. These bond angles are about 104, 105 degrees. You can see that the lone pairs will occupy the same plane. That will always be the case. It didn't matter which of these I replace with a lone pair, they will always occupy the same plane to maximize the distance between them. Okay? So those are the three subsets of tetrahedral. Tetrahedral, trigonal pyramidal, and then the bent shape. Let's go to our next domain, which was trigonal bipyramidal. Now, when we start playing with trigonal bipyramidal, let me get it to where I have the axial position, if I can. I think it's hard to rotate. There we go, we're getting close. There we are. Okay, so here's my trigonal bipyramidal shape, or electron domain geometry. It has several subsets, several. The first one is called trigonal bipyramidal also. When all five of these domains are shared, it's trigonal bipyramidal molecular geometry as well. If we replace, though, with a lone pair, let me point out that the lone pair went into the equatorial position. That's not arbitrary. That is where these things go. They go into the equatorial position because that allows the lone pair to be the farthest away from its neighbors. In class, I hope to bring the models out and show you why this is true. But for now, look at the new geometry. This is called a distorted tetrahedron, but more commonly we refer to it as the seesaw shape. You can kind of see here as I rotate it, it looks like the old playground teeter-totter, up and down, up and down. Okay? It looks like these two are straight across. That's not really true. There will be a slight bend to these here, so they're no longer, depending on your point of view here, they used to be 180 from each other, but now they're going to be, in this point, a little bit greater than 180, and then if you look at it from this point, a little less than 180. But they're going to be squeezed a little bit. and then everything else gets squeezed together as well. These two will now be a little closer than 120, and they'll be a little bit greater than 120 here. But again, we call this the seesaw geometry. If I take away another, oops, let's take that away. Let's take another one away. If I take away another shared pair and replace it with a lone pair, again, it went into the equatorial position. See that in the equatorial position. This new molecular geometry is called T-shaped, and it's called T-shaped if you just look at what's left behind, terminal atoms and central. You can see a definite T there. Now this T-shape on the screen looks like 90 degrees. Again, this is not going to be actually 90 degrees anymore. We're going to see the big fat lone pair squashing this shape, so it's kind of like hold your arm straight up, make a T with your body, and then kind of let your arms droop a little bit. That's what this T would be closer to being, because these big fat lone pairs are pushing down. So far for trigonal bipyramidal electron domain, we've had the trigonal bipyramidal molecular geometry, we've had the seesaw molecular geometry, and then now we've had the T-shape. So let's actually remove a third shared pair and replace it with a lone pair, and you can see we get yet another subset of trigonal bipyramidal. We call this linear. The equatorial position has now been totally used for holding lone pairs. This molecule is actually, or this geometry is actually fairly common in organic chemistry. Trigonal bipyramidal, but it's linear. And believe it or not, it's symmetrical. It's non-polar when you have this geometry, because these three lone pairs around the center cancel each other, and it leaves you with something very symmetric. So those are the geometries, molecular geometries, that I want you to be responsible for under the trigonal bipyramidal electron domain. All right, let's get rid of those and put back our shared pairs, and then let's add one more to get to our final geometry here. This is the octahedral electron domain. Now this is a very symmetrical shape, as I mentioned before. So the first molecular geometry is also called octahedral, non-polar if you have this geometry. Let's replace now with a lone pair. Again, it will go into the equatorial position. Let's take one away first. All right, so we can see it went into the equatorial position, but let's kind of look at what's left. What is this weird shape? Kind of turn it around this way, and let's kind of look down the axis here. Well, we added it to the equatorial position, but can you see how through the ultrasymmetry of this shape that it actually now sort of became redefined as the axial position in a way? So if you look down the new axis of the lone pair, you can see that this is a square, and it's three-dimensional. There we go, that's what I wanted. It's three-dimensional, so we have a pyramid again, but this isn't a triangle-based pyramid, it is a square-based pyramid. So this is called square pyramidal molecular geometry. All right, if I take away another and replace it with a lone pair, we get back to another shape that we've sort of looked at. Let's look down that axis again, and you can see that we're left with a square in the plane. So this is called square planar molecular geometry. This is the subset. This is, believe it or not, symmetrical. Most of the time when I had a lone pair in the structure showing you these pictures, we were making polar substances because we threw the symmetry off. This is one of the shapes that you actually get to keep the symmetry when you add lone pairs. It takes at least two to do that. And that's really the only geometries I wanted you to know for the octahedral domain. Again, we had octahedral molecular geometry, we had square pyramidal molecular geometry, and we had square planar. Technically, we could keep going, we could keep adding lone pairs, But we start revisiting some of the same shapes that we've had before. Can you identify that shape? Yep, that's T-shaped. If I did it again, look what we've made again. We back down to linear again. So we start seeing some of the same things. And these shapes aren't quite as common, because if I start packing in all these lone pairs into the equatorial plane here, the repulsions here are quite significant, and this is really an unstable arrangement. That's why I'm only making you learn octahedral, square pyramidal, and then the square planar for this domain series. All right, well, that was just a quick way for us to go through and discuss each type. In class, you should have been given a chart to fill out, either as you watch this video or as your teacher goes over it. That really will help you summarize kind of what we've gone through here. And then soon we'll be building our own shapes, either with marshmallows and gumdrops or with Play-Doh or whatever. If at the end of those activities you still aren't sure how to assign geometries, make sure you come by and get some help, and we'll work through it.